I'm Guevara Noubir. I'll be talking about detecting and canceling jammers that have reasonably high power using machine learning techniques. And this is joint work with my student, Nguyen. So I'll start a bit with the motivation for this problem. Then I will very briefly talk about related work. Then I will talk a little bit about the details, the theoretical foundations, the machine learning aspect, and then the cancellation algorithm, and then go into the evaluation, some conclusions. So I used some fairly old slides that I had for these, the next two. And this is to contrast with what's happening today. So, but I guess this is almost 10 years ago, this slide. You see some Russian jamming system there. And the idea is that jamming is fairly easy to do, and it still has significant impact on many systems. You can buy jammers on eBay. You can find YouTube videos that show someone how to take the magnetron from a microwave oven and repurpose it so you can use it as a high-energy RF gun. There are SDRs. There are lots of sophisticated things that in academia, at least, we've been exploring in terms of cross-layer attacks and so on. But at least at that time, the argument was, it's not only military. We don't see that much. There's also a lot of interest in other applications. You can have denial cascading effects. You can have the rogue infrastructure that will start with jamming higher, newer generations of systems. As you've seen last few days, people have been talking about this. In the US, the government started responding to these things as they saw more and more of these instances. So in 2012, there was the FCC started a hotline or tip line and so on. And even a hotel chain was fined because they were jamming Wi-Fi. So that was what people will be talking about at the time. But then, yesterday, I just did a Google jamming this, and you find, so this topic of high-power jammers is back. You see it, everyone is jamming, everyone, drones having issues. Even there is self-interfering or self-jamming and so on. So the high-power jammers is a problem that has always been around and most likely will stay there to some extent. But there is a need for some techniques that can handle these high-power jammers because communications are more and more important and used in a variety of systems. So now how do you deal with jamming? There are various kinds of techniques. But this problem has been studied for many, many years. You could imagine that you transmit a higher power, but it's not really the best way. You could start using channel coding so you can be resilient to jamming, or you go to spread spectrum techniques. There are variations on them. They have overhead in terms of what spectrum, amount of spectrum you need to use to be able to evade the jammer in some way is an overhead. There are also techniques that rely on pilots. So I'm showing here Wi-Fi. You have these 4 pilots. Some systems will have many more to be able to be resilient to jamming. So here I'm going to summarize a little bit what some of the related work in the context of use multiple antennas, because using multiple antennas can give you a lot of benefits. So you don't need much more spectrum. The overhead will be significantly lower, and you can null a jammer. And I'm going to come back to the technical details. So if you look at these systems, so we wanted to kind of organize this discussion so that we can relate it to our work. Systems that can detect a jammer, so they can deal with it explicitly. The cancellation can be done by relying on some reference signals like pilots, or you could rely on something mechanical. Then systems that rely on machine learning, and then systems or techniques that were really investigated in a real setup. And in a kind of summary, in fact, maybe just for the sake of time, so the system that we developed is exploring the use of machine learning. So this is the first system that will do both detection and cancellation. That is implemented and demonstrated that it works, and it does not require any pilots, and it does not require any moving of parts. In fact, if you can move parts, you can have really significant capability to cancel jammers. Years ago, about 10 years ago, we had a paper showing that you can reduce the impact of a jammer by almost 50 dB. So that's 5 orders of magnitude. But it takes some time because you need to move these antennas in a way that you can cancel, and it's also, you have moving parts, which are not really good. Okay, so how does this whole thing work? If you have one antenna to receive, and you have a legitimate user transmitting, and you have an adversary. So you'll get this first formula. Okay. This thing doesn't show. Anyway, so you get R1. This is what your single antenna would receive. And you get the signal S that is being transmitted by a legitimate user multiplied by the channel gain from the sender, this first antenna, to the receiver, plus the jammer signal multiplied by the gain from the jammer to the receiver, plus some noise, N1. Now, you don't know what's the signal being transmitted, and you don't know what's the jammer signal. You have at least two unknowns. You're not going to be able to solve that equation. If you add a second antenna, R2, you would have now two equations, the gains from the sender to the first antenna and the sender to the second antenna. These are two different gains, and similarly for jammer, and then you have that noise. So you have two equations, two unknowns. You could possibly solve it if you know if you know HS1, HS2, AJ1, AJ2, or some variation on that. So in here, what we do, we ignore N1 and N2. We assume that we are in a situation where we have the jammer power is quite high, so the noise is not that big. If the noise was similar to jamming power, we can deal with it in different ways. So you can see, for these two equations, if you take the second one and you divide by AJ2, so you have a term of J, and then you multiply this thing by AJ1, you subtract from R1. So R1 minus AJ1 over AJ2 times R2, you would get rid of J. And you have something proportional to the signal, which you know how to deal with. So it's fairly simple. What you need to know then is the ratio of AJ1 over AJ2. If you knew that, you can solve this. So this is really the fundamental thing about all these multi-antenna systems. And there are two components, because these are complex numbers. You need the ratio, AJ1 over AJ2, the amplitude of that, and then you need the phase, which we call phi J1 minus phi J2. If you knew these two pieces, you can solve the problem. And what we do here, this whole machine learning, is about determining that. So how does the system work? You have your RF front end. You have your two antennas. They'll give you R1, R2. These are the samples. They're IQ samples, so they're complex numbers. We pass them by first block that will allow us to predict the phase difference. You remember, there's a phase difference and the amplitude ratio. These are the two things we want to know. There is a second block that allows us to say, is there a jammer actually or not? In fact, it will tell us if there is a signal, if there's a jammer, it will predict it with machine learning. And the last part is computing the ratio of the amplitudes. If we have these three things, we just apply the formula that I showed before, and we can solve this problem. So the whole thing is about how can we how can we build these three blocks? And that's what I will show in the next few slides. So the first block, we wanted to output, try again. Okay. So we want to output two things. We want to know if the first, so it outputs two phases, phase 1 and phase 2. And in addition to that, it will output 2 bits. The first bit will say that the first phase actually corresponds to something. It's not just junk. And then the second one does the same thing for phase 2. So 2 binary outputs and then 2 phases. And how we build this, well, we take 128 samples, IQ samples, from each of the antennas. You stack them. Now, why 128? Well, we tried with the smaller and bigger. 128 seemed to be the one that works best. Bigger means it's going to be slower, more complex. Smaller, you don't get as much accuracy. And then in between, this whole thing, there's nothing really special. So these are just the typical CNN layers with ReLU activation functions, max pooling, with different kinds of configurations. And then you have a fully connected layer at the end before the final one that outputs these 4 outputs. So, of course, we tried with the more layers, less layers, and so on, and this seemed to give the best results. The loss function incorporates 2 things. One is the loss in terms of phase, and here we use mean square error. And for these outputs that are binary, so we use binary cross entropy for the loss function, and we combine them with some coefficients and so on. So nothing really magical. The key thing is that we wanted to explore, can we come up with solutions based on machine learning? And like everyone using machine learning, not really having to think too much about it, it gives us something that would be reasonable. So that block will give us the difference in terms of phase. The next block, the next piece is we want to know the ratio of the amplitudes. You remember we need this AJ that's really there in the top. That ratio of... Okay, so this ratio here, remember that's what we wanted to calculate. That's related to the ratio of the energies that are received that correspond to the jammer. And then take a square root of that. So we want to estimate the energy coming from the jammer. And there are a few cases. We're really also interested in the case when there's a collision, when the jammer is really interfering. So when that is happening, the amount of energy we're getting is the sum of the energy of the jammer and the legitimate user. And you just have to estimate the energy of the legitimate user and subtract it from the total energy. And this algorithm that basically does that by looking at few cases, and it has to consider, well, did the jammer start before or after, and so on. But again, it's like a basic block, not extremely sophisticated. And the final thing, once you know the ratio of the gains and the phase difference, then that algorithm that might look quite long, but in fact, it just considers the few cases that you have. If we only have a jammer or the sender that is transmitting, we need to know, well, is this a legitimate signal or not? And how we do it, well, you try to decode it. If it works, then you know it's fine. If it doesn't work, you know this is a jammer, and you don't have to do anything. If they're interfering, it means that both the jammer and the legitimate signal are there. So we have our indicators from that block that gives us two binary outputs. We need to know which one is corresponding to the jammer and which one is corresponding to the legitimate one, and that we just track. And the last thing is the last case is when there is nothing. So it's fairly just reasonable. Now you know that machine learning, if you're doing like I don't know, face recognition or something like this, and you have one error in 1,000, you'd be very happy. If you have one error in 100, you'll still be very happy. But the RF signals, if you have one bit in error every 1,000 bits, your system is not going to be very good. You need to fix that. So what happens is that these outputs of these machine learning systems, they're not very robust. So if you look at the blue plot, that corresponds to just taking the outputs and using them directly. You'll see here, as a function of signal to jammer ratio, in log base, the bit error rate is quite, it's not that good. If the power of the jammer is the same as the power of the receiver, you would be at 10 to the minus 4 bits. So your probability is low, but it's not really that good. If you start smoothing the outputs of the machine learning, you see that now even if you are at minus 15 dB, which means that the adversary is, let's say, almost, I think, okay, like 30 something, almost 40 times stronger in terms of power, you can still be at 10 to the minus 5 bit error rate. So averaging has a significant impact on improving the performance. So we compared our solution to other techniques, for instance, to techniques that rely on pilots. And we compared them also in these contexts where you have a challenging channel, like a Rayleigh channel. And what we see here is that, first of all, if you don't have any protection mechanism, your bit error rate will be 0.5, and you're not going to get anything. If you use one of these existing techniques, you would need to have 50% of what you're transmitting to be redundancy to match the performance of our system. So our system basically is quite good, at least in this context. Then we looked into, well, these models that we came up with. As I mentioned, there's nothing really magical about it. There's just like very pragmatic way of designing them. And of course, one would imagine designing something better in the future. What if we use some existing architecture like ResNet or VGG16? Would they do well? And what we see here, so the orange shows the error. They do reasonably well, but if you look at the computation effort is significantly higher. So they're just overkill for this task. If you take some of the techniques that were like CNN also based modulation recognition, they're quite efficient, but they don't really work that way. So it seems like what we designed made sense and gives you good performance and also good, both in terms of computation and in terms of accuracy. So we did a lot of evaluations, and I will go over them quite quickly. So in all of them, the blue line here is going to correspond to if you don't use the protection, and the others are our system. In these 4 ones, so there are different modulations and also for different separations. So if there's one thing that one has to remember with this whole system is that if the jammer and the sender are aligned, there's nothing you can do with it because these 2 equations I showed to you, they're going to degenerate and they're going to be collinear, so you're not going to be able to solve that. But for different phases, you see that we can get almost like 20 dB improvement, meaning that the adversary could be transmitting 100 times more power, and we can still get a bit error rate that's extremely low. So I think given that I'm getting close to the limit, I'm just going to, so we also compare if you use AWGN versus a modulated signal. And as you might know from information theory, the AWGN jammer is the optimal one. And as you'll see here that it does better than the modulated jammer, but still our system gives you at least 15 dB better performance in various scenarios. We also evaluated our capability to detect, and you see the confusion matrix shows you that you're not going to make errors. If there is noise, it's going to tell you there is noise. If there is a collision, it will tell you that with quite high probability. If there is single transmission, there's some 5% probability that it will make a mistake. We evaluated the system with over-the-air communications, and again, you'll see that it significantly outperforms if you don't have this protection. We also evaluated that against the power adaptive, so jammer that changes its power, or that stops and starts again, and so on, and again, we see quite significant performance. So to conclude, this work was to explore if you can use machine learning to do some of the tasks that were done with algorithms, typically with multi-antenna systems, but instead of having to take care of all these cases and load computation, just push it to the machine learning. And it seems to work quite well. It's also significantly better than existing techniques that rely on pilots, because pilots, once you interfere with them, they're going to create a lot of issues. But at the end, I think this is just the beginning to start designing systems that can be quite efficient at countering jamming without having to maybe do the do all the work in terms of mathematics. I'll stop here.
Thanks, Guevara. We have time for a few questions.
Yes, okay. Yes, Constable from Princeton University. Very nice talk. What are your thoughts on blind source separation techniques and adding perhaps for jamming purposes?
Yeah, for counter jamming. Yeah. I think that is the trend, and this work is within a kind of that context where you don't use a reference, you don't use a pilot, so you want to solve any problem. And my view, at least, of machine learning is somehow, maybe it's a negative view, is that you don't want to spend too much time looking for all the corner cases and so on, and you train for it. And if you have the computation capabilities, I think it works quite well. Of course, there are problems that we know very well that can be solved. I don't know, for example, if you're going to do decoding, I don't know, LDPC code or polar code, you just go, they're designed for an algorithm. For these cases where jammers can behave in so many ways and so on, and they coming from different angles, it seems to be a reasonable way of, I think machine learning seems to have a potential in there. But, it started about quite, at least the last 5 years has been significant amount of work in that space, yeah.
So is it fair to say that if we do blind source separation, the computational complexity increases, but perhaps the number of averages that you need might go down?
Yes, I think it would be fair to say that because all these, they're quite dense, these neural networks, so they are reusing the information that you give them in so many ways. I think it makes sense to make that assumption. Yeah.
Thank you.
Thank you.
Hi. First off, really interesting talk. Thank you very much. I was just wondering if you've tried any adversarial attacks on this system, so trying to craft a jam signal that's misclassified as non-jamming, or perhaps add a signal that then makes your system discard the legitimate signal?
Yeah, I think it's a very good question. It's very reasonable. Yeah, so we didn't do that, but I think that's something necessary. If you want to deploy something like this, you'd have to take care of all these things because it is designed for something adversarial. It should not just look at one aspect and miss the other ones. Now, in the context of machine learning, you might know there's all these certified models and so on that there are methods how to deal with adversarial input. So I think one possible next step could be to incorporate that kind of work here. Yeah.
Yeah, great. Thank you.
We have time for one more quick question.
So that's quick. Thank you for the talk. Just to better understand the approach. So that CNN model tries to estimate the phases on a per symbol basis, or it just needs to? And if that's the case, what's going to be the computational complexity?
It doesn't do it on a per symbol level. So these phase differences, they're not going to change because this is the phase difference between the jammer to the two antennas. For these phases to change, the adversary has to move quite a bit or has multiple antennas. So we, as you know, two equations, two unknowns, if you add another transmitter or another jammer and so on, this would not work. And it is averaged over 128. So the CNN takes 128 samples, but then you saw that lambda that does the smoothing, and that's, I think, the one that works quite well is 10 minus 2, 10 minus 3. So so there's quite a bit of average.
And so the scenario is a static scenario, no mobility.
Yeah, not much mobility. I mean, if you move quite slowly, it should be fine. But if you teleport, then it would not work.
Thank you.
Thank you.
All right, let's thank Professor Noubir again for a great talk.